Hello everyone, you're watching the Space Channel. In the world of show business, there are outrageous stars who always end up in the headlines. It seems astronomy has its own representative who loves the spotlight. This object consistently becomes a source of sensational news, linked to the idea that life might exist somewhere in space beyond planet Earth. That object is the exoplanet K2-18b, which orbits the red dwarf K2-18, located 124 light-years from Earth. It was discovered in 2015 with the help of the Kepler space telescope. This exoplanet follows a short orbital period of 33 days and is situated a little more than 21 million kilometers from the star at the center of its system. Planets that orbited the Sun at such a distance would have no chance of normal existence. Gas giants would immediately evaporate, while rocky planets would be nothing but huge incandescent lumps. However, the activity of red dwarfs is lower than that of Sun-like stars. Therefore, in the case of K2-18, no belt of extremely high temperatures lies 21 million kilometers from its surface. Instead, there is a zone where the existence of life is possible. Because of this circumstance, exoplanet K2-18b ended up in the limelight. The lens of the Hubble Space Telescope was directed at it. For a while, Hubble studied the exoplanet, and in 2019, scientists, after analyzing the data, saw traces of water vapor in its atmosphere. This was the first time in astronomical history that researchers detected signs of water vapor in the atmosphere of a planet outside our solar system, located in a life-friendly zone. Yet the capabilities of Hubble turned out to be insufficient for investigating K2-18's atmosphere in detail. Generally, scientists can infer the composition of remote planetary atmospheres using spectroscopy. The essence of the method is that different atoms and molecules interact differently with electromagnetic radiation passing through them, leaving a characteristic spectral fingerprint somewhat reminiscent of a barcode. In the laboratory, spectral lines of atoms and molecules are very sharply distinguishable, but on cosmic scales, they look more blurred. For this reason, information about the composition of distant atmospheres reaches ground-based and orbital telescopes in a highly averaged form. Telescopes with large mirror diameters are required to focus the incoming radiation and obtain spectra from distant cosmic objects. The Hubble telescope became the first space telescope that met these requirements. Thanks to it, the discovery of exoplanets and a broad-brush determination of their atmospheric spectra became possible. However, Hubble operates in visible light and cannot overcome the observational barrier caused by redshift. Radiation from distant objects is stretched to longer wavelengths, shifting from the visible into the infrared. Therefore, the ideal telescope for studying remote exoplanets must not only have a large mirror, but also operate in the infrared range. That role is fulfilled by the James Webb Space Telescope, JWST, which went into service in July 2022. One of its designated targets was K2-18b, and almost immediately, researchers began receiving promising data that potentially indicated the presence of life on this exoplanet. In September 2023, the JWST detected molecules of carbon dioxide and methane in the atmosphere of K2-18b. Their presence allows scientists to ask whether living organisms are present on the planet. Yet another question remains unresolved. To which class does the exoplanet belong? A rocky super-Earth or a gas giant? The point is that in the solar system, planets are clearly divided into groups by surface character and size: terrestrial, rocky planets, and gas giants, including Uranus and Neptune, often singled out as ice giants. At the same time, K2-18b does not fit neatly into either type. It occupies an intermediate position. The planet's radius reaches about 16.5 thousand kilometers, and it has a mass 8 times that of Earth. There is, however, one marker that lets scientists assign a planet to a group: the presence of ammonia in large quantities. This is typical of gas giants and not found on rocky planets. The James Webb Telescope did not register ammonia in significant amounts in K2-18's atmosphere. Thus, researchers are leaning toward the idea that this exoplanet is rocky. Yet, due to the temperature regime, it probably resembles Saturn's moon Titan, which has a dense gaseous atmosphere and a liquid ocean beneath its surface. Owing to the planet's dimensions, a hypothesis has arisen about what K2-18b might be like. The theoretical model has been dubbed a Hycean, hydrogen ocean world, a potentially habitable world covered by an ocean lying beneath an atmosphere rich in hydrogen compounds. Let us return to the discovery of methane and carbon dioxide. It should be noted that on Earth, these molecules can be synthesized not only through biological processes, but also in inorganic reactions, particularly during volcanic eruptions. That is, carbon dioxide and methane are significant but not absolutely conclusive markers of life. A molecule is needed that would indicate this fact more reliably. Such a molecule is dimethyl sulfide, DMS. On Earth, it is produced exclusively by living organisms. Scientists began searching for evidence of its presence in K2-18's atmosphere. Eventually, in April 2025, a paper appeared in which researchers, having analyzed data from JWST, concluded that the exoplanet's atmosphere indeed contains dimethyl sulfide with high probability. As with the discovery of water vapor, this finding was the first of its kind. Spectral analysis showed that the concentration of DMS in K2-18's atmosphere is tens of times higher than in Earth's air. Because the compound is short-lived and breaks down within days, its accumulation at such levels indicates active life processes by a large biomass of primitive microorganisms. As noted above, on Earth, dimethyl sulfide arises solely from organic reactions. However, in space, there are also inorganic sources of this compound. Traces of it have been found in cometary material. To confirm that DMS is an unambiguous marker of life, scientists must conduct experiments to prove or disprove the possibility of synthesizing this molecule abiotically from inorganic precursors. For future studies of K2-18b, the success of the project depends on how frequently JWST can observe it and on the subsequent analysis of the resulting data by scientists. Still, humanity will never know exactly what lies beneath the exoplanet's atmosphere until it finds a way to send a spacecraft there.